Jai Hind, myself Neha Garg, and today's topic is application of operational amplifier. This topic has been taken from the subject Fundamental of Electronics Engineering. Subject code is BC201. So, why closed loop is required in op-amp? Like if we have this circuit, this is V1 and this is V2 and this is our output, and A is the gain of the op-amp. Then output will be V2 minus V1 times of A. So this is the open loop configuration. Open loop configuration means there will be no feedback from the output to the input side. And op-amp is basically a difference amplifier which amplifies the difference between the two input signal like V1 and V2. The difference will be V2 minus V1. So op-amp will amplify the difference of these two input signals. And this is useful when the noise is applied at both ends. So this noise will be acting as a common mode signal and it will be cancelled out. So that's why this is the use of the difference amplifier. So why we cannot use the open loop configuration as a amplifier? Because in open loop configuration we know that the voltage gain of the op-amp is infinite. Voltage gain is infinite in ideal case. So if we see the voltage gain A is infinite here, and we can write A is equal to V0 upon V2 minus V1. So if this A is infinite, for any value of this V2 minus V1, the output will be high because the gain is infinite. So if V2 minus V1 is 1 microvolt, output will be maximum. If it is 2 volt, then output will be maximum because the gain is infinite. So for any value of the input signal V2 or V1, the output will be maximum. That is the saturated value. And that saturated value depends upon the supply that we connect here, VCC and minus VCC. That lies in between 12 to 15 volt for IC 741. So for any values of these V1 and minus V2, the output will be V0 always be 12 to 15 volt. That is the saturated value and that is the maximum value. That's why in case of the open loop configuration, output is fixed. That is the saturated value. So we cannot use open loop configuration as an amplifier, and we require the closed loop configuration. In closed loop configuration, there will be a feedback from output to the input side. We have taken the some part of the output signal into the input signal, and this feedback must be in the negative side. Means there will be a negative feedback, because in negative feedback gain will be decreased. Overall gain will be decreased in closed loop configuration, and we can have a flexible gain. We can because in open loop what we have seen that a gain is infinite, gain is maximum, and so for any values of V1 minus V2, output is maximum. That is at the saturated value. So for getting by taking the negative feedback, this V1 minus V2 gain will be decreasing. Gain will not be infinite, it will be decreased, and it will be controlled by the factor RF, and this is R1. RF is the feedback resistance and R1 is the input resistance. So it will be regulated by, gain will be regulated by by the value of RF and R1. So we can have a different values of the output signal, and we can design any amplifier of different gain value, like gain may be taken as 10, 100 or 1000. So now we are designing an inverting amplifier using a closed loop configuration. So for this purpose we can see minus plus. So this is our output, this is Vi, this is R1 and this is RF. So here we can see this RF and R1, these are acting as a for the negative feedback. We can see this this RF connects the output value of output voltage to the input side, and plus terminal, that is a non-inverting terminal, is grounded and the input is given to the inverting terminal. That's why it is acting as a inverting amplifier. Now we can see this VA is a virtual ground. VA point is the virtual ground point. And due to virtual ground concept, the value of VA is 0. and ideal op-amp does not draw any current. Ideal op-amp does not draw any current. Ideal op-amp does not draw any current. That's why there will be no current here, and all of the current, this I1 will be passing through this feedback path, and I1 would be equal to IF, and I1 will be equal to Vi minus Va upon R1. Similarly, Va minus V0 upon Rf, and value of Va is 0. That's why it will be like Vi upon R1 is equal to minus V0 upon Rf, and we can write it as minus Rf upon R1 multiplied by Vi. So here gain is equal to minus Rf upon R1. So in open loop configuration, gain was infinite. So for any values of the input signal, the output gets saturated, that is the plus VCC or minus VCC. But in a closed loop configuration, we have taken the inverting amplifier, and in this the gain becomes minus Rf upon R1. So we can change the, if Rf is 10 and R1 is 1, so gain will become minus 10. If we change the value of Rf to 100 and R1 is 1, then it will be 100, gain will be 100. So by changing the value of Rf and R1, we can change the gain of the amplifier, inverting amplifier. And here we can see this minus sign indicates that if the input signal will be in this way, the output signal will be in this way. There will be a 180-degree phase shift here. So next is the non-inverting amplifier. So non-inverting amplifier, we have like, this is negative feedback, and here we have given the input signal to the non-inverting terminal. This is the feedback resistance, this is the input resistance, and this terminal is grounded. This is output voltage. Here the negative terminal is grounded and the supply is given to the positive terminal. That's why it is called as the non-inverting amplifier. And now due to virtual ground concept, VG, VA is equal to Vi. And ideal op-amp does not draw any current. Ideal op-amp does not draw any current. Does not draw any current. That's why I1 is equal to IF. I1 is equal to IF. Now value of I1 would be equal to 0 minus Vi upon R1, and this will be Vi minus V0 upon Rf. So we can arrange the value and we can find V0 is equal to 1 plus Rf upon R1 multiplied by Vi. So here gain is equal to 1 plus Rf upon R1. So this is the value of gain here, and we can see the gain is coming as positive. So if this is the input signal, output signal will be in this way. There will be a phase shift of 0 degree here, and the value of gain is 1 plus Rf upon R1. So we can change the value of Rf and R1 and we can have the different values of the gain. So this is the non-inverting amplifier in closed loop configuration. Now the unity gain follower. So unity gain follower means the gain of the amplifier will be unity, and this can be designed by using the non-inverting amplifier. Like this is the circuit for the non-inverting amplifier. This is Rf, this is R1, and this is Vi, and this is grounded. Now in this circuit, if we put Rf is equal to 0 and R1 is equal to infinite, then we will have the circuit like in this way. This will be like this, and this will be Vi. Now if we take the formula for this, V0 is equal to 1 plus Rf upon R1. This has been we have derived in the last slide. So here we will put the value 1 plus 0 by infinity. So we can write it as V naught is equal to Vi, or we can write V naught upon Vi is equal to gain is equal to 1. So this is the unity gain follower. We have put the RF0. RF0 means it will be short circuit, and R1 is infinite. So it will be open circuit. So this part is open here. So it will not be written here. So only this circuit will be there. This is the circuit for the unity gain follower. So what is the advantage of the unity gain follower? If the gain is unity here, it will act as a buffer. Main application is act as a buffer. It provides a high input impedance and low output impedance, and it is generally used for the impedance matching. Impedance matching. Next is the inverting adder. Inverting adder adds the two or three different voltages, input signals, or inverting adder means adder is applied at the inverting terminal. Plus terminal is grounded, and all the input voltages are given to the inverting terminal, like in this way. This is V1, V2 and V3. This is R, this is R, this is R, this is RF. So here we can see in the inverting terminal, we have applied three voltages, V1, V2, V3, and three signals have been applied, and the plus terminal has been grounded. So it is working as an inverting adder. Now, due to the virtual ground, VA is 0 due to virtual ground. And ideal op-amp does not draw any current, so it means there will be no current here. And now this current is I1, this is I2, and this is I3. This current is passing through this feedback resistance. So I1 plus I2 plus I3 is equal to IF. So I1 is V1 minus VA upon R plus V2 minus VA upon R plus V3 minus VA upon R is equal to VA minus V0 upon RF. Now we can put the value of VA here 0. So we will be having like this V1 upon R plus V2 upon R plus V3 upon R minus V0 upon RF. So here we will be having V0 is equal to minus RF upon R, V1 plus V2 plus V3. If RF is equal to R, then V0 would be equal to minus times of V1 plus V2 plus V3. So this is how this is acting as a adder, and that is the inverting adder. Means V1, this provides a sum of the V1 plus V2 plus V3. But negative sign indicates the if the inputs are in this way, output will be 180-degree phase shift. After that, non-inverting adder. So in non-inverting adder, we will be having circuit like in this way. This is the R1 and this is RF, V0, RF, R1. And since this is a non-inverting adder, we will apply input voltage at the terminal, at the non-inverting terminal. Here we can see this is a non-inverting terminal, and we have applied the adder circuit V1 and V2 here at this point, and in inverting terminal has been grounded. So we will find the voltage here VA, and this is our VB. Here this VA is not grounded, so we will have to find the voltage at the VA terminal. So we will apply KCL at VA terminal. So for applying KCL, this is I1 and this is I2. Sum of I1 plus I2, all incoming current will be 0. So I1 would be equal to V1 minus VA upon R plus V2 minus VA upon R is equal to 0. So we can find the value here. V1 plus V2 is equal to 2 VA. So VA is equal to V1 plus V2 upon 2. So we have find the value of VA here, and now due to VG, due to virtual ground, VA is equal to VB. So, and ideal op amp does not draw any current. So, this current I1 is equal to I2. We can write it as 3 and this is 4. So, I3 is equal to I4 and this will be equal to V1 plus V2 by 2. And I3 would be equal to 0 minus VB upon R1 and this will be VB minus V0 upon RF. Now we can write it as 0 minus VB is V1 plus V2 by 2 upon R1 and this is V1 plus V2 by 2 minus V0 upon RF. So by cross multiplying this, we can find the value of V0 in terms of V1, V2 and R1 and RF. So this is how it acts as a inverting, non-inverting adder. After that, the subtractor. So for subtractor provides a subtraction of the two input voltages. So like we have to, this is our feedback path V0, this is RF, this is R1 and this is, so we can apply V1 and V2 here. So here we have applied direct V2 at the non-inverting terminal and now due to the virtual ground, due to VG, this VA is equal to V2 and this current I1 is equal to I2. So I1 is equal to I2 because ideal op amp does not draw any current. So I1 would be equal to V1 minus VA upon R1 and this is VA minus V0 upon RF. VA की वैल्यू लिख दो V2, V1 minus V2 upon R1, V2 minus V0 upon RF. Now we can find the value of V0, we can cross multiply this and we can find the value of V0 here. So we can, and also this is our circuit number 1 and we can also modify this circuit in this way. We can apply the divider here like in this way, V0, RF, this is R1, V1, V2, R and R. Here we can find the value of VA R upon R plus R multiplied by V2. So V2 by 2. This is our VA and this is our VB. So VB is here V2 by 2. Now this current we can find out, this is I1, this is IF. So I1 is equal to IF and I1 would be equal to V1 minus VB upon R1 and here it is VB minus V0 upon RF. Now we can put the value of VB and VB is equal to VA, that is equal to V2 by 2. So we can put the value of V1 minus V2 by 2 upon R1 is equal to V2 by 2 minus V0 upon RF. So now we can cross multiply this and we can have the value of output voltage. So these are the two circuits that we can use for as a subtractor. Now the difference amplifier. So difference amplifier is the same circuit as we have discussed in the last slide. Like this is the circuit V0, this is RF, this is R1, V1 and this is grounded, this is V2, this is R and this is R. Here we can find the value of VA. So VA would be equal to R upon R plus R multiplied by V2. We can find the value like in this way. We can apply KCL here. The sum of all incoming current at this point will be 0. So we can find the value of VA in this way. Now this VA would be equal to VB. So VB will also be, it will be V2 by 2. Now ideal op amp does not draw any current, that's why I1 is equal to IF. I1 is equal to IF. I1 would be equal to V1 minus VB upon R1. and here VB minus V naught upon RF. So V1 minus V2 by 2 upon R1 is equal to V2 by 2 minus V naught upon RF. So here we can find the value of V naught by cross multiplying this. After that, integrator. So integrator provides the integration of the input voltage. Like in this, we are having this circuit minus plus, and here there will be a capacitor in the feedback path, and this part is non-inverting terminal will be grounded, and this is R1. So in integrator, what we have done, we have replaced the RF with the CF value, CF resistance, and this is our output voltage. So output voltage is the integration of the input voltage. Now this is the VA point. So potential at VA is 0 due to virtual ground. Because this terminal is grounded, that's why the potential at VA is 0 due to the virtual ground concept. Now this is your I1 and this is your IF. So I1 would be equal to IF. Because ideal op amp does not draw any current, that's why I1 is equal to IF. And now how we can find the value of I1? That's equal to VI minus VA upon R1. And now the current through the capacitor, it is given by C dV naught. This is VA minus V naught upon dt. This is the current through the feedback capacitor in the feedback path. Now VA is 0, so we can write it as like VI upon R1 is equal to minus C dV naught upon dt. So VI would be equal to, we can write it as minus RC dV naught upon dt, or we can write it as dV naught upon dt minus 1 upon RC VI. So V naught is equal to VI upon RC dt. So this is how V naught provides the integration of the input voltage, and this integrator has different applications. If we apply the square wave as an input signal, so output waveform will be triangular waveform. So like if we apply square waveform, sine wave, this is our input VI. VI is equal to Vm sin omega t. So output will be equal to minus 1 upon RC VI dt. So it will be minus 1 upon RC. VI is this. So Vm cos omega t minus sin plus. So output waveform will be like in this way. It will be a phase shift of 180 degree. So 90 degree phase shift. So it will be in this way. This is our output, because plus here, so amplitude will be positive in this direction. So this is the analysis with the sine wave. And if we give the step signal, step will be converted into ramp signal. Like we have signal like in this way. This is T and this is Ft. So this will be A. This is A. This is a step signal. We can define it as T is equal to, it is A, and T less than 0, it is 0. This is our Ft. In this way, this signal can be defined. And if we integrate this A, like in this way, V naught is equal to minus 1 upon RC VI dt. So it will be equal to VI is A dt. So minus 1 upon RC AT. So this is our ramp. AT is step signal is converted into ramp signal. Similarly, ramp signal will be converted into parabola. Ramp into parabola. And square waveform will be converted into triangular waveform, because square waveform is just like in this way. Square waveform is made with the help of the step signal, and the step is providing the ramp, like ramp in this way. This signal is ramp. That's why this square waveform will convert it into triangular waveform, like in this way. This is our input and this is our output. So integrator basically it provides the different waveforms, like triangular waveform is providing ramp signal, parabolic signal, sine will be converted into cos, and also it acts as a low pass filter. Low pass filter means if we like its cutoff frequency is FL. So it will pass the signals whose frequency will be less than this FL. That's why it will be called as the low pass signal. And after that, differentiator. So differentiator provides the output voltage, that is the differentiation of the input voltage, like in this way. Here positive terminal is grounded, input is given to the inverting terminal. In feedback part there will be a resistance RF, and here there will be a capacitor, and this will be your output voltage. Now the voltage at VA would be equal to 0 due to virtual ground. And now ideal op-amp does not draw any current, that's why this I1 is equal to IF. I1 is equal to IF. So here we can find the value of I1 like dV minus VA upon dt. And here we can find VA minus V0 upon RF. Here the value of VA is 0. So we can write it as V0 is equal to minus RC dV0 upon dVi upon dt. So that's why this circuit acts as a differentiator, and differentiator provides the like ramp signal into step. It converts the ramp signal into step, and parabola to ramp, square signal into square to spikes, and this is used as a high pass filter. So next applications will be discussed in the next lecture. Thank you.